Right, welcome back. In the last lecture, when we started talking about energy and power and everything, I noticed afterwards that I had totally the wrong units in an example. So this example is just the quick calculation of power. We talked about it last time, and I noticed that I had this in units of newtons, and I didn't even mention it. I was too busy looking at the numbers and not the units, but we know that power should be in units of watts. So I just wanted to point that out really quick before we started moving on to the topic of this lecture. So I fixed it in the lecture notes. You can download that and it should be fine. Um, so that being said, all right. So just for the quick summary from last time, we talked about work, power, potential energy, and kinetic energy. We have equations for all four of those. Now we can move into the work kinetic energy theorem. So we're going to do something a little mathematical here. This is a lot of fun. It's sort of what got me into physics, being able to play with the mathematics and do all these cool calculations without numbers. So really what we're going to do is make mathematical statements, and we don't even need numbers to understand what's going on with the math. So beginning with Newton's second law, which we know is F equals ma, we can actually start from F equals ma and build or derive the work kinetic energy theorem, this whole idea that work equals kinetic energy. And we talked about this last time briefly. We said that, whatever amount of work is needed to take an object from rest and get it up to speed, whatever the work is to do that, that's the amount of kinetic energy it's going to have. So these two are in fact related. And believe it or not, we can start with F equals ma and wind up with W equals Ke. So let's do it. This will be fun, I promise. So we can start with F equals ma, Newton's second law. It's so unassuming. And we can multiply both sides by d. It's an equation. Whatever we do to one side of an equation, we have to do the other. All right, we multiply both sides by d. If you're watching and paying attention, you know that that's already work. Work equals force times distance. And apparently that equals mad. So we have this distance on both sides. We got force on the left here. So we can go ahead and make a note of that. All right, but now we need to do something more with this m times a times d. Well, you'll remember from way back when we were talking about projectile motion and things being dropped. Well, if they're dropped under acceleration, right, acceleration due to gravity, we know that we can calculate that distance by 1/2 at squared. Well, we have a different way to write distance now, 1/2 at squared, and we have a distance right here. So let's actually make this substitution. Okay. So you'll see everything here just wound up right here. Right? This is just d. We just made that substitution, no big deal. Now we can actually rearrange a few things. So we have this t squared. Let me change my color here. We have this t squared. We also have this a and another a floating about. Now notice all this crap is multiplied together. So we can reorder it any way we want to. So what I'm going to do is I'm going to have these two a's that are multiplied together. They're just not right here the way it's written. So what I'm going to do is I'm going to move those together and just write them together. So we have an a squared t squared. Okay, everything else is fine. It can just hang out. Well, since they're both squared, I could just smash those two things together in parentheses and pull the square out, right? Because really, I've essentially just undistributed the square. Well, now I have this AT in here, and that also looks familiar. Well, you'll also remember from way back when we were talking about kinematics, velocity is just acceleration times time. So since I have this acceleration times time here, I could just plug in velocity. So when I make that substitution, look at what I get. I get essentially FD equals 1/2 mv squared. Well, we know that work equals FD, and we know that 1/2 mv squared is kinetic energy. And since all these things are equal, right, we can just grab the things on the end. They're all equal. So work equals kinetic energy. So this is the cool thing that I like about physics and thinking about things mathematically is we literally started with F equals ma, inserted what we knew through this process, and then we got a new relationship out of this. I mean, going from Newton's second law to the big work kinetic energy theorem, I think is pretty cool. That means Newton's second law had that in there. It was just hiding. So Newton's second law is actually quite powerful because you can get so many things out of it. And you can start from F equals ma and pretty much build every equation we use in the first part of this course. I don't know. I think it's neat, but I wanted to see that you can actually start with Newton's law and build the work kinetic energy theorem, which means it's hiding in there, and it's been hiding in there since we started talking about Newton's laws. So the work that we're talking about imparts kinetic energy to an object. That's all we've been saying. Bringing something up from rest, doing work to do that means you're giving it kinetic energy. But if an object already has an initial velocity, so maybe it's already moving and we want to speed it up even more or slow it down a little bit. So we can't talk about absolutes anymore. When we do work to change that velocity, right? And if we change the velocity, we're changing the kinetic energy. We got to talk about it in terms of a delta, right? So the work done on an object, if it were to have an initial energy already and we want to change it, the work done is actually just a change in kinetic energy. So this is the real work kinetic energy theorem. So the work done equals the change in kinetic energy. Remember, we said that work is a transfer of energy or a change in energy, not just an energy itself. So previously, when we said work equals kinetic energy, that's in this one special case where the object starts from rest, essentially. Starts from rest. This is physics. We want to be able to use this everywhere. So we need to change our definition to actually include the situation where we might have an initial kinetic energy. So the work kinetic energy theorem is the change in kinetic energy. Now, when we talk about the work kinetic energy theorem, we're also talking about the net work. So all the different forces are doing work. You know, you could have some kind of object with 20 different forces acting on them or on it. So the whole idea is essentially you got to think about the net work that's being done by all these forces doing work. Okay, so the net work done is going to imply that we're thinking about the net force that's going to act over a distance, which is going to give us the change in kinetic energy. So net work is dependent on the net force. So let's think about what this means. So if you push a box across the floor, you must act against friction. Yep, we've all pushed something across the floor at some point, I hope. If not, I invite you to push your book across your desk. You're going to feel friction. So you have to act against friction. That means there is a net force, but there's also multiple forces going on. Now, if we look at this diagram over here, we obviously have the weight of this crate or this box, right? It's coming down. It's not flying through the floor or anything, which means something's got to be holding it back. We know that's the normal force. And we know from Newton's first law that these two things are canceling each other out because it's setting at rest. So these two things have to be equal. But guess what? We don't care what's going on in the y direction. The y direction does not matter here. Right? Because when we push something from side to side, we don't care about what it's doing in the y direction. All we care about is the force that we're pushing with and the thing that's opposing us, the friction. Okay, so that's really our net force in the x direction. We can even label it x direction if we want to. So we have this push in the positive direction, and the friction is obviously opposing us in the negative direction. That's why it's a minus on the friction, because it's taking away from our push, right? Well, this is our net force, which means that's what's going to be considered in the work kinetic energy theorem. So we have the difference, when we plug it in, we have the difference of these two forces. So we take the push, we subtract off the friction, and whatever is left over, which would be this, whatever's left over is the thing that's going to be doing the work and changing our velocity of this box. So only part of the total work changes the object's energy, because we're subtracting some out. The rest is due to friction, right? We're losing some of that input due to friction. And if you've ever like rubbed something really hard and caused friction, then you get friction burns, right? If you do it on your hands. So essentially, part of our work done, we're just losing it to heat, right? It's an efficiency issue. So we actually have this heat loss, which is essentially just ruining our efficiency. If we could take all of that work and put it into just the motion of the object, we'd be 100% efficient. But since we're losing some, we're not quite 100% efficient. So if the force of friction equals the push, then the net force will be zero. Right? So this becomes a Newton's first law thing. So if that force of the push is equal to the force of friction, well, then, yeah, Newton's first law kicks in and there's no net force. So if that's the case, then if we were to subtract them, if they're equal and we subtract them, then there's 0 newtons in there. So that means this whole piece for the work calculation, if they're equal, becomes 0, which means 0 joules of work's being done, which means no change in the kinetic energy or the velocity. So if there's no net force, there's no change in kinetic energy. Does the object have kinetic energy? Yeah, it's moving, right? It's got a velocity, but it is not a changing velocity. So if everything is canceled out, even though the object is moving, the work done 0 because it's not effectively changing anything in the problem. All the work you put into it to keep it in motion is being lost somewhere else. So you're in 0% efficiency pretty much. We can actually take this idea, the work kinetic energy theorem, and generalize it to more than just kinetic energy. So the whole idea here is essentially when work is done by an outside force, we say that essentially work equals the change in energy. So this is just the work energy theorem. And you can think about this in terms of like kinetic energy, potential energy, nuclear energy, electrical energy. I mean, the list goes on. There's so many things that we could have. But the whole idea is essentially if any of these were external and they were doing work, some of these will be changed because they did work. Some of these will get changed because work's happening to them. The whole idea of work, though, is it's not a form of energy. And I've said this many times, but it is a way of transferring energy. That's why I always write the work leads to a change in energy. So we're converting it. All right, so let's look at this example. It's not even a math problem, really. It's just a conceptual problem. So can an object have energy? And can an object have work? We've sort of talked about this already, but yes, an object can possess potential energy relative to its position. Remember last time we talked about wherever you put your origin is going to dictate how much potential energy an object might start with. So yes, an object can have potential energy, an object can have kinetic energy, but it cannot have work. Work is the change in the energy that it has, right? Work is an energy transfer. Okay. It's like saying a person can have an age, but they can't have aging, right? They have an age, but they don't have a change in age. The aging process just sort of dictates how the thing they have changes over time. So that's a loose metaphor of how you can think about this. But with the conservation of energy, the whole idea of like, work can change energy into different forms. We can actually get to one of the coolest ideas in all of physics, and it shows up everywhere, and it's like a super fundamental rule. So we can understand the processes and changes that occur in nature if we talk about the changes in energy in these processes, not necessarily how much energy is in the process, but how it changes. So the study of various forms of energy and their transformations from one form to another has led scientists to one of the greatest generalizations in physics. And this is super important and will pop up a lot. This is the idea of the law of conservation of energy. So energy cannot be created or destroyed. It can be transferred from one object to another, or it can be transformed from one form into another, but the total in your system never changes. So when a whole system is considered, right? So remember when we were drawing boxes for Newton's third law, talking about our system, we had like an orange in a cart with an apple, and the apple was pulling, and we would draw the box and say that's our system. That's what we're talking about here. When a system is considered in its entirety, there is one quantity that isn't created or destroyed, and that would be the energy in the system. We'll think about this with this circus diver over here in the image. You'll notice that this diver starts with all potential energy. Totally makes sense. The dude's not falling, so he has no kinetic energy. His initial velocity is 0 meters per second. His initial kinetic energy, 0 joules. No motion, no kinetic energy. But notice he has 10,000 joules of potential energy here. It's 10 kilojoules. And let's total this up. So let's do potential energy plus kinetic energy. Look at what we get. Shocker, since kinetic energy is 0, when we add these together, we still get 10,000 joules. of energy. It's just all potential energy. Right. Well, now he's going to jump. Okay, let's look at this first point in his trajectory. Well, he fell. That means he's reduced his height relative to the ground. Okay, so he's shaved some height off. If he's removed height, he has less gravitational potential energy. And that's reflected here in the numbers. He only has 7,500 joules of potential energy because he's lost some height, right? Less gravitational potential energy. He's also in motion now. So instead of a V initial, we'll call this V1. He actually, since he's fallen, he has some velocity now, which means he also has some kinetic energy. Okay, let's think about the total energy of the system. So we're going to add up all of his potential energy and all of his kinetic energy. Well, if we add this together, it turns out we still get 10,000 joules of energy. That's what he started with. Now look, in his halfway point, he's got even more kinetic energy because he's speeding up, right? So we're up to 5,000 joules of kinetic energy because his velocity is increasing. He shaved off even more height, so he has even less potential energy. So now it's evenly split. Halfway down, it's split between potential energy and kinetic energy. But if we add those two things together, the total is still 10,000 joules. We can do the same thing for the next step. He's got even more kinetic energy and even less potential energy. But if you add those two up, it's still 10,000 joules. And notice here at the bottom, when he's pretty much at the ground, he has no height. He's pretty much at the origin. He's lost all that gravitational potential energy because he's removed the thing given it to him. He's removed all this height. But that energy had to go somewhere. So where did that original 10,000 joules of potential energy go? Well, you can see it went to kinetic energy. So all of his GPE was transformed into kinetic energy through this process. And again, if we add up the total, we still get the same thing, 10,000 joules of energy. Here's the idea of the whole conservation of energy and changing energy from one form to the other. You can see over this process, we go from 10,000 joules of gravitational potential energy, and over time is converted to 10,000 joules of kinetic energy. But notice through the whole process, the total remained 10,000 joules. Let's think about this. Just because this might come up. This isn't like a real example. This is just sort of a point, but I wanted to do an example for him. So consider a hammer striking a stake. And we've talked about this before with Newton's third law. So most of the energy will be transferred to the stake, right? The stake will sort of get pushed, even though it's applying an equal and opposite force, it'll still sort of get pushed into the ground because the momentum of the hammer is transferred. Most of the energy transferred to the stake, but if you've ever hammered one of these in, you know that your hammer will, if you hit it frequently enough, your hammer will get a little hot or warm due to the hitting, and then you'll also hear a sound. So both of those are kind of like friction. They're sort of taking energy out of the system. So we have the initial energy of the hammer as it comes down. Most of that goes into the energy that's given to the stake, but we also have some of that energy going into sound, and some of that energy going into heat, and some of that energy going into just other things we're not considering right now. The idea here is that if all energies are accounted for, then the total energy will remain the same. So here, whatever you started with, all the energy of the hammer, if you could account for everything, so you could end with the exact same number. The point here is sometimes there's so many tiny little energy losses that you can't keep up with all of them. If you were to actually calculate, the total energy of the hammer and then calculate the energy imparted to the stake later, if you could measure all those, it might look like there's a little less, but that's just because you can't calculate and pull in and measure all the different energy losses. Some systems you can. Not saying you'll never be able to do this, just, in everyday life, sometimes it's hard. It's hard to keep up with all these. But just be aware, if you can do it, the total energy remains the same. All right. Let's look at this example here. So this one is pretty in-depth, and I think we'll end on this one example for now. So acrobat Art, who has a mass of M, stands on the left end of a seesaw, and acrobat Bart, who has a mass of big M, jumps from a height h onto the right end of the seesaw. Okay? In the ideal case where all inefficiencies are neglected, okay, so we're going to assume that there's no loss to sound or heat. How does the potential energy of Art at the top of his trajectory, so he is going to fly up here, how does his potential energy compare with the potential energy of Bart just before he jumps? So right now, essentially. So clearly, judging from the floor and the height here, Bart has some potential energy. So how is this potential energy, when this circus trick is done, how does this potential energy relate back to Art's potential energy? That's our first question we want to answer. Second question which is just another sort of math demonstration, is we just want to show that Art's height that he achieves, we can actually write it without knowing any values. We don't need to know right now what M is. We don't need to know what big M is. We don't need to know what the height is. We just can show that H art, there we go, the height that Art will travel up, we can actually represent it with just letters. We can represent it symbolically. So we want to show that this is the case. So we can essentially solve the problem without numbers and then plug them in later if we get them. And that's actually the whole point of C here is, once we do the calculation without numbers, if we know them, if we know Art's actual mass, and if we know Art's actual mass, which is 40 kilograms and 70 kilograms, if we know the height of the initial jump, we could actually show that Art rises an actual distance of 7 meters. So here. Okay, so don't get confused there. That's 7 meters, and then this is actually mass. Okay, so let's give this a shot. So to answer this first question, if everything is taken care of, we don't have to worry about any of these inefficiencies. So if Bart jumps, what would happen is Bart's potential energy, if he jumps, would essentially, when he gets to the bottom, becomes all kinetic energy. And then that kinetic energy would be transferred over to Art, right, which is going to launch him and give him some kinetic energy, which is going to make him fly upward. But that kinetic energy is going to start turning into gravitational potential energy. So when Art gets to the top, he's lost his kinetic energy that got him there, but he's gained a bunch of potential energy. So the point of this is essentially we can skip the line, we can skip ahead. So we know that there's going to be lots of energy transformations. but we just want to relate these two things. The idea here is if we can ignore all the inefficiencies, all of Bart's potential energy is going to become all the potential energy for Art. So this energy gets transferred to this potential energy. Okay. And that's, of course, if everything stays perfectly perfectly efficient. Well, that's nice. So let's use this statement, since we know that these two things are going to be equal, right? Let's use this statement and actually calculate Art's height. Okay, well, we can plug things in. We know the potential energy is mgh. We know Bart's mass is big M, weighs more, so capital M. So mg, then his height, which is going to be h Bart, right? We don't know any numbers, but we know this has to be his gravitational potential energy. We know that at the end of this problem, it's got to equal Art's gravitational potential energy. So he weighs less, so his mass is going to be lowercase m times g times the height that he travels, h Art, which would be this piece here. Now, just to show what is going on with the math here, oops, big M, G, H, Art, little m, G, H, Art. You'll notice that there's a G in both of these, so we can divide both sides by G, which will get rid of that G. And that'll leave us with big M, HB equals little m, HA. Now we want to write this in terms of Art's height. So we want to solve for this term. Well, we can divide both sides by little m, right? There's lowercase m here, and that's what leads us to this final point. Art's height is just going to be this ratio of Bart's height, which makes sense, right? We have two different heights, and it's just going to be scaled by their masses, right? If Bart's heavier, that's going to impart maybe a little more to Art's height. Maybe Bart is jumping off from a not so high point. The whole idea here is essentially we're just going to use the masses to scale the final answer, right? So one height, Bart's height, it just needs to be multiplied by some ratio because everything's conserved, and that'll give us the new height of Art that we're looking for. Now, if Art's mass is 40 kilograms and Bart's mass is 70 kilograms, and the height of the initial jump was 4 meters, okay, now we have everything. We have both masses, check, check. We know Bart's initial height. We can plug that in, and it turns out Art will fly 7 meters vertically. All right, so I will stop there. This hopefully is shorter than the previous one. This is just to show the conservation of energy and the whole idea there of like the work kinetic energy theorem, just discussing transferring some type of energy into another type of energy. And hopefully these examples have illustrated that well.